Professor Peter Palffy-Muhoray, who is coming from Kent State University in Ohio. Let us welcome our speaker.
Okay, thank you. It's a great privilege to be here, and I'm really impressed that so many of you managed to come back. When I was a graduate student, often I didn't always go to the last talk. Anyway, I'll try to tell you about liquid crystal elastomers and light, and this will be not a very deep talk, and hopefully it'll be even a little light-hearted. I don't have anything to do with clickers, though, so I apologize for this. I basically want to talk about three things. What are liquid crystal elastomers? What do they do to light? And what does light do to the elastomers? And then we're obliged to have some kind of summary. So, okay, first question is, what are LCEs? Now, there have been many talks already on elastomers, and typically, all the speakers would begin with some definition. And this reminded me of this picture of different people tend to see different aspects of LCEs. So I looked on the web to find this picture, and there are many, many pictures, but none of them have women in it. So I think that this speaks well to women's vision and perspective. Okay, so many of what I have to say, much of what I had to say you've seen already before. So these are orientationally ordered materials, so we have to have an order parameter. So we have the Q tensor you're all familiar with. And it's convenient if the system is uniaxial to express this as a scalar order parameter and the pneumatic director, which is the direction of average orientation. Scalar order parameter takes some values between 1 and minus a half. Disordered system has an order parameter equal to 0. Minus a half means that all the molecules are perpendicular to the symmetry axis lying in the plane. Now, because we're talking about light-matter interactions, we need to talk about the dielectric tensor. And this is simply, if you just derive from first principles the polarizability of the bulk, you'll find that the dielectric tensor is a linear function of the order parameter tensor. This is a scalar, the average isotropic average dielectric constant, and delta epsilon, again, is a scalar, the dielectric anisotropy. And so there are two things that one needs to worry about. One is the energy density of the electromagnetic field in the material, because that can drive things. And the other thing is light propagation. We've already seen Maxwell's equations. In a non-magnetic material, you can write it like this. Epsilon tensor is lurking here, essentially determining what happens. Now, if one looks for plane wave solutions of this form, we can rearrange this a little bit. So this is the propagation direction. And what one finds then is we have to solve this equation. And the point I want to stress is that epsilon is a material property, and the refractive index is an eigenvalue. So those are different things. And whereas this thing will change depending on the propagation direction, polarization, and so on, epsilon is what describes what the material does. Okay, pneumatic liquid crystals. Well, again, you've all seen this free energy many times. This is Landau expansion. Now, here I don't have gradient terms. So these terms are just a trace of Q squared, Q cubed, and so on. So these are independent of the director, and you can write it simply in terms of the scalar order parameter. And so you get the usual first order transition. And I won't bother to differentiate between Tc here and the transition temperature because they're practically very, very close. The effect of an external field is important. An external field comes in like this. So this is coming from the expression for the energy density I showed you before. And in terms of the director, we have this coupling. And if delta epsilon is positive, the material wants to line up with the electric field. So essentially, all displays are based on this term. Now, there's two things that are worth pointing out. One is that this critical temperature, if you look at molecular theories, this critical temperature is proportional to the number density of mesogens. And so we have already heard about this from Mark and others. So if you dilute or increase the concentration, you're changing Tc. And so if you dilute and you reduce Tc, that's essentially the same as increasing the real temperature. The other useful thing to meditate on is how big are these constants. And you know, if you try to do dimensional analysis, what can you do? Well, we have nothing basically. We have this critical temperature and the molecular size. And this is an energy density, so the coefficients pretty much have to be kTc over a molecular length cubed. And that turns out to be about 10 to the 6 pascals for most pneumatics. So that's a good number to keep in mind. Okay, elastic solids. So free energy density is just Young's modulus times the strain squared. And the modulus, Young's modulus turns out to be 3 times the cross-linked number density times kT. So that's a good thing to know. If you heat up a rubber, modulus increases. One can estimate one of these from the other. Okay, so now we have liquid crystals, we have at least pneumatics, elastic solids. And now if you apply an external stress to rubber, then you have to add this term, just like we had to add the electric field term to the order parameter expression. And so what is Young's modulus typically? And here's an experiment measuring Young's modulus for a rubber band. This turns out to be about 10 to the 6 pascals. So that's about the same magnitude as the coefficients in the Landau expansion for pneumatics. And this gives you a sense of how stiff these materials are typically. Okay. Now, so as Dejean originally proposed in this beautiful work back in '75, if you put these two aspects together, you have the liquid crystal bit, the elastomer bit, and there is a coupling between the order parameter and strain. And you can sort of see it from this kind of picture. Obviously, if you change the degree of order here, that's going to pull these crosslinks together and push the perpendicular ones further apart. So there's this coupling term. And a nice way of thinking about this, I think, is just to note that as far as the liquid crystal is concerned, this new term looks no different than the electric field term. So strain behaves in the same way as the electric field dyad does. And similarly, as far as the elastomer is concerned, Q behaves the same way as an external stress does. So I think that's a useful way of thinking of these materials because it gives you an intuitive sense of what happens when you put different excitation on there. So for example, if you were to heat the sample, as we've heard already, then that changes Q. That essentially is equivalent to a stress, and you find a shape change as a consequence of that. And similarly, mechanical strain, if you stretch the elastomer, has the same effect as a strong electric field. And now I'll come back to how strong an electric field, but it turns out that it's pretty significant. Now, in addition to elastomers, I want to talk about glasses, which are essentially very similar to elastomers, but have a higher crosslink density by a really significant factor, as we heard already. So the main difference is very high crosslink density and consequently very high modulus. Okay, so that's kind of background. Now, what do LCs do to light? So that's the first of the two topics I want to talk about. And first, what do these things look like? So if you make a typical side chain elastomer, so these are materials that were developed by Heino Finkelman. They look kind of like Jell-O, but a little stronger. And so they're transparent materials typically, but they're birefringent. So between cross polarizers, they look like a crystal, except you can tie knots in it. So that's kind of interesting. Now, where does the birefringence come from? So if the field is perpendicular to k, then you can throw away the second term in the Maxwell equation, the wave equation, and you can rearrange things to look like this. Epsilon is just this linear combination. So it's the identity plus the order parameter tensor written in terms of the director and the scalar order parameter. And then if you just solve this equation with this epsilon, then you find that you get two values of the refractive index for the electric field parallel to the director or perpendicular to the director. So the greater the order, the greater the difference between these two guys. In the isotropic case, these things disappear and these two become the same. Okay, good. Now, what are the effects of stress? Well, if you just stretch the material, you're applying a longitudinal stress that increases the degree of order if the director is already aligned, and that increases the birefringence. And this is a little experiment that was set up for an outreach exercise by Jake Fontana, who is an old student here somewhere over there. So Jake made this in, I don't know, half an hour or something. He was very able to get things done quickly. And so you strain the material, and you see the typical oscillations in the transmitted intensity between cross polarizers. Of course, you have to be concerned about the sample is getting thicker at the same time, but nonetheless, it's also showing the change in birefringence. What are applications? Now, Heino Finkelman had this really fascinating idea to make a contact lens, a birefringent contact lens. And you think this is crazy because you'll see two images, but apparently this is okay. Our brains are quite happy to process two images and choose the one that you want to see. So I thought this was kind of an interesting idea. Okay, I don't think they're available on the market yet. Now, sometimes you have monodomains. The sample I showed you is monodomains. Sometimes you have polydomains, as you heard already, and we can have gels and networks. And so this is kind of an amusing little experiment of just taking a monodomain sample and swelling it, in this case, with chloroform vapor. So just put a container of chloroform into a chamber and see what happens. And at first, nothing happens, but then the shape changes rather dramatically. You can see a contraction along this direction and a widening in the perpendicular direction. And the sample breaks up into polydomains and scatters light. As more solvent vapor is absorbed, again, it's like changing the temperature, if you like, then an isotropic region appears, and eventually the whole sample goes isotropic. So this is a kind of a fairly standard story. The initial formation is polydomain, then it can become a monodomain, and vice versa. So polydomains typically scatter light if the domain size is in the range of optical wavelength. And of course, one can also use light scattering to probe the structure of the domains, which are typically anisotropic themselves. And then modeling, this is kind of a tough problem. So Eugene Turentyev did some early modeling of fully developed LCs. We were looking to see what happens on the early stage when the material is made and it's just starting to cross-link and form nematic domains. And these are simulations by Misha Pevny, who's also here in this august body. Now here's a really interesting material. This is a physical gel made by Julie Cornfield at Caltech. And what she did, she simply took a tri-block copolymer where the end groups were insoluble in 5Cb, the nematic liquid crystal 5Cb, in the nematic phase. So if you mixed these two things together at high temperature, you got a relatively nice, uniform, viscous mixture. But when you cooled it down, the insoluble polystyrene end groups tried to microphase separate, and they formed a physical cross-link, and so formed a physical gel. And this, again, was a polydomain material but you could align the domains with an electric field. And so you could make a kind of a scattering, non-scattering shutter. All right, and I want to say a few words about lasing in cholesterics. So this is kind of a fun story. So cholesteric liquid crystals have a periodic structure. Molecules are chiral. They like to not be exactly parallel, but tilt with respect to each other. So one ends up forming, if you just typically put these in a container, you form a structure where the director is rotating in space, forms a helical structure. And of course, that means the dielectric constant is periodic. And then by Floquet's theorem, that means that there is a band structure in the system. That is, there are regions of parameter space where there are no stable solutions. And so these materials spontaneously self-assemble to form a photonic band gap structure. And you get these really highly reflective, iridescent reflections. So, and then this was an image laser written in a cholesteric cell. So these are self-assembled photonic band gap materials, and you can do lots of interesting things with them. And the way it works, sort of, is, again, if you go back to Maxwell's equation, now epsilon here is varying in space, so you have to go into some rotating coordinate system to solve for the eigenvalues. Turns out you get two branches for two circularly polarized modes. And one of these branches, n squared, becomes negative in some region. The band edges are determined by the principal values of the epsilon and the pitch, the period of the cholesteric. And now, if n squared is negative, the index obviously is imaginary, and the reflection coefficient has magnitude 1, right? This is just the complex conjugate of that. That means all of the photons come back out. So you shine a plane wave, any kind of light on this material, there's an evanescent wave inside, but every photon that goes in there, in principle, comes back out. So, and this is what happens inside the cholesteric, not just at the front surface, but everywhere, essentially inside. So imagine now that you have a molecule that has an atom in an excited state, and this atom wants to kick out a photon. Where does the photon go? Well, it's going to go where there's the most space for it. It's going to go into an empty state. And where are the empty states? And that's described by the density of states. So that the emission rate is proportional to the density of states is Fermi's golden rule. The density of states is not too difficult. It's just dk over d omega. So this is a wave vector magnitude. This is a frequency. And you can write the magnitude of k as omega n over c. And if you take the derivative, you get two terms, this guy and this guy. Now, this is interesting. So this is the derivative of n with respect to frequency. And now, if you imagine that n squared becomes 0 somewhere, as in this picture I've showed you here, then it must have this form when it crosses 0. That means that the derivative will have a 1 over n term in it, and this thing blows up. So that means that at the band edges, there is a divergence in the density of states. So that's where all the photons want to go. And so if you have lots of excited states, you'll have stimulated emission, and because you have this divergent density of states, all the photons come out there. So one has stimulated emission and lasing without any cavity, without mirrors, nothing. It's all distributed cavity effects in the material. So you can take an ordinary cholesteric cell and you shine a pump laser on it, and you'll see beautiful laser light coming out on both sides. So it's coherent. You can see interference fringes. So it's a kind of a self-assembled laser. Now we're talking about elastomers, and Heino made some cholesteric liquid crystal elastomers, and turns out you can make these lathes. And so if you apply a strain to these, you're going to change the optical properties, specifically the pitch, and therefore the reflection band, therefore the place where the density of states diverges. And basically you can tune the outcoming laser light by simply stretching the sample. So it's a kind of a tunable rubber laser. Okay, moving on. More recently, we had a visitor, Daniel Wenslick from Rudolf Zentel's group, and he brought some cellulose samples, and cellulose makes a liquid crystal network, and it turns out that you can make that laser as well pretty easily, just pretty much the way the other stuff lays. Cellulose is interesting because there's lots of it around. Okay. So I think I'll move on now and talk about the complementary part of this problem. What does light do to liquid crystal elastomers? And there are basically two scenarios that one can think of. One can think about direct forces and torques from light. Light can simply push and pull and twist things. So this is associated with momentum transfer. Or we can think about light affecting the order parameter somehow, and then the consequences of this produces internal stresses, torques, strains, and so on. So let's think about the first part first. So if you just have an, I don't know, air, vacuum, metal interface, and you shine light on that interface, say a plane wave, the photons all carry linear momentum h over lambda in the wave vector direction, and that'll be reflection, and there'll be radiation pressure pushing this interface away from the source. If you put an absorber here, blackboard or something, do the same thing, the photons get absorbed, they don't get reflected, but there's still momentum transfer, and there's radiation pressure pushing the absorber away. Now, if you put a dielectric here, a piece of glass or a glass of water, you shine a plane wave on it. Interestingly, you get a force pulling the interface toward the source. No gradients here, just a plane wave. And this is because when a photon goes inside, okay, the refractive index is bigger than 1, the wavelength gets shorter, momentum increases, photon kicks back on that interface. As it gets more momentum, it pushes back on the interface. Okay, so that's more or less how direct forces work. And torques are similar. So photons have two sources of angular momentum. There's spin, h bar k hat, and orbital, which is just r cross p, the usual kind of angular momentum we associate with classical mechanics. Now, Betz showed back in 36 that if you shine circularly polarized light on birefringent plates, you can exert a torque. So that was a nice demonstration of angular momentum carried by light. And you can do the same thing with cholesterics. So when circularly polarized light shines in a cholesteric, it exerts a torque. Now, if circularly polarized light shines on a mirror, a metal mirror, it does not exert a torque. Okay? Its spin remains the same, direction of propagation changes. But it cannot couple, it cannot exchange momentum. But with cholesteric, it can because of the chirality. And so light exerts a torque, and the same handedness of light is reflected. Okay, and orbital momentum, that's kind of the same story, except here, imagine a pneumatic, which is oriented homeotropically, and in comes now a plane wave. And imagine a plane wave, imagine a photon hitting a periscope in a submarine. Photon comes in here, hits the mirror, pushes on it that way, goes up, hits the mirror, comes up. So there's a net torque on the periscope due to the momentum transfer with the mirrors. And the molecules are just like that, and so light exerts a torque on these molecules, the orbital angular momentum. Okay. This was shown by Alfred Saupe, who submitted it to Phys. Letters, was promptly rejected. He put it in his jar, and it stayed there for a long time. Okay, so now the quantities, both the stress and the torque, have the structure of d dot E, and for light to do anything, this energy density has to be comparable to Young's modulus. So now you see the problem. We have to make d dot E equal to 10 to the 5th pascals. And if you put the numbers in here, it turns out that even if you have a 1 watt CW laser focused to a square millimeter, you only get a millipascal. So you have to have huge, huge fields to be able to overcome the restoring force of the network. So practically speaking, we don't have fields big enough, and this is not the way to go if you want the elastomers to sing and dance. Okay, so what's the way to go? Well, the way to go is to change the order parameter. And so light can change the degree of order. This produces stress, strain, and a shape change. And then one can ask, how does the optical field change the order parameter? And there are many different ways. That can be linear absorption or nonlinear absorption and simple heating, laser heating if you like. So one effect is just heating, changes the order parameter. Another is the disruption or creation of order through photoisomerization. And as we heard already, not only is trans excited into cis is possible, but the other process is also possible. So there are now materials where when you shine light on the band form, you get a straight form, and you can use light both to disrupt and also to create order. Direct optical torque we talked about, but the fields are too small, so we ignore that. And then there are some beautiful mechanisms that I'm particularly fond of, but I don't think I have time to talk about. But essentially, based on the idea of Landauer, it's possible to use light to bring about continuous rotation of dye molecules in one sense in an amatic. Okay? And these are important and fascinating processes, but I'll not say anything more about this now. If you're interested, I'll be happy to talk about it at the end. So these are the two things I want to focus on. And so let's go. So what kind of shape changes do we expect? And again, we've heard a lot about this. So typically, if you reduce the degree of order, we expect a contraction along the director. So this dimension will get shorter, and this dimension will get larger in order to conserve volume. And here's this iconic little clip from Heino Finkelman's group of this material when you heat it up. So now it's well aligned. You heat it up. Then there's a contraction along the director, and it gets wider the other way. On the other hand, if you have a non-uniform change in order, and again, we heard about this as well, if you decrease the degree of order here, but not here, then you will get a bend instead. And not only a bend, it turns out that if you have a contraction along the director, which is more or less into the board here, then you must also have an expansion in the perpendicular direction. So you get this typical saddle shape as a consequence. So you get contraction here and elongation the other way, and you get the saddle. And well, I don't need to say anything about this. We've already heard two talks discussing how absorption and the optical field inside these materials is non-trivial and leads to interesting dynamics. But here's one thing that might be interesting. So this is a little experiment, just shining light on a dye-doped liquid crystal elastomer. And so there will be a reflection. The surfaces are nice and smooth. But of course, due to the effect of light, the surface will not stay smooth. But as you increase the intensity, you see this diffraction pattern, and then one can try to work backwards and try to figure out what the surface relief is of the elastomer as a consequence of light shining on it. And so as the intensity goes up, if the modeling is good, then one develops a surface structure that looks something like this. Moving on. So the classic experiment to indicate this new coupling between light and matter is by by Mark Warner and co-workers and Heino Finkelman. This was 2001, showing how UV radiation can give rise to contraction in materials where azo dyes have been covalently bonded into the elastomer network. We did some, this is Tomiki Ikeda and Yanlei Yu, who then made these beautiful networks. These are polydomain networks which curl up, and these are fascinating because they curl about an axis perpendicular to the polarization of light. And this is because it's a polydomain material, so the domains where the director and the dye absorption moment is in this direction, they will contract, the others much less so, and you get this kind of curling up. And then you can unfurl the material by irradiating it with visible light, which then drives the cis-trans transition. So this is really beautiful results. We then we just dissolved some azo dyes into elastomers, and you've seen this already. And so this is a little faster, but of course, people can always make things go even faster. And so here's the 270 hertz. The main point, I think, is that once the light hits the backside, then it drives it the other way. It's not just relaxation. I think it's being slapped from both sides. So this is work done by a group of the Air Force, Tim Wydridge, via Tim Bunning. And of course, they're interested in flying. And so there was work fairly recently to see if one can make artificial wings and make these things fly. And this just shows some particle velocimetry showing the airflow. But I don't know what the status is, whether the thing can fly or not. But we know that it can swim. This is our first goldfish that we tried to make. And we're really holding it by the nose down here. But it is clear that it can at least pump water, okay, even if it's not swimming rapidly. There's some other strange stuff that one can stumble onto. If you float a little circular disk of elastomer under a laser beam, you find that it swims away from the light. And that was pretty perplexing, and to some extent, it's still a little perplexing. We put it on some other material, and it wasn't square, but it still swims away from the light. Okay, now this is really beautiful work by Casper Van Osten and Dick Brower and others, and you've already seen this, but I think this is really marvelous work. So you need to break reciprocity, otherwise the scallop theorem prevents you from pumping water. So this is a printed cilia with two different kinds of dye. So you see bending, which is non-reciprocal, and this enables the system to pump light. And this is inkjet printed, so I think this is really a marvelous piece of work that has potentially lots of applications. And you've seen this beautiful movie as well. I don't know. Yeah. Well, Dick told you in detail what happens, but I'm just really impressed both at the idea and the performance of this device, but also with the graphics. This is really impressive. All right. Now here's another interesting material made by Ikeda and Yanlei Yu. So this is a robotic arm. And again, it has two kinds of illumination, and you can make it do really clever and impressive things. So I think this is really a marvelous piece of work, indicates the kinds of things that are possible. But to me, one of the nicest things ever was the slide-driven motor from Ikeda, and again, Yanlei's lab. So this is just a crystal elastomer, possibly a network, on a flexible substrate. You shine UV light here, visible there, and the thing goes around. So to me, this is pretty much magic. Okay. So Now there's another interesting device which is very similar, which is called the Thermobell. How many people have seen this? Nobody. It's amazing. You can buy one. I mean, they used to be around when I was a graduate student, and they vanished. You can buy one again. You put it in your coffee, and it goes zzz. You know, either way, one way or the other way. It's reversible. Anyway, the wire here is nitinol, which undergoes an austenite-martensite transition, and we've already heard about the parallels between liquid crystal elastomers and this transition. Okay, so we were really intrigued by this, and this is work with Xiaoyu Zhang, whose name I forgot to put on there, and I apologize. And Mark Warner was involved as well. And so it turns out that one can actually model this system pretty successfully, because we really wanted to understand what makes it tick. And if you do that, essentially use an energy minimization scheme, you can calculate pretty much everything. So what we did was we put in a natural curvature, which is due to radiation. You shine light on this thing, it wants to bend, right? And so that natural curvature is this bend. So this is what the curvature wants to do over here. And then one can do numerics and solve for everything. And then the question is, why does it go around? And there are two ways of thinking about it. You can have a careful look, and you see that the filament here is further away from the center than here. So if the forces, at least the relevant components of the forces, are comparable, then there will be a net torque turning it that way. If you don't like that, you can look at it right where the filament comes off the wheel, where the curvature is given. The curvature is the same as the curvature of the wheel. And it turns out that then you only have to worry about point torques due to local bending. And even though the curvature is the same, there's a natural curvature here, which means there's a greater local torque at this point where it's being heated than at this point. So that's why it goes around. There's still a question of angular momentum transport. Where does the angular momentum come from, right? It has to come from somewhere. And so we meditated on this. And so imagine, look at this little model, and imagine that it's symmetric. The centers are the same height. There's some tension in the filament. And if you now look at this, you see that this guy, the vertical components of these two tensions cancel out. So we just need a horizontal force to keep it going that way. Here, the same story. So all is well. Now you bring the UV source and you deform the filament here. I exaggerated a bit. But you can see here we have a downward force, but up here we don't. So we have to lift up on the holder here to keep the thing from coming down. And the opposite happens here. Here we have an upward force, but here we don't have a downward force to balance it, so we have to pull down on the thing. So we have to essentially exert a torque by the table, and angular momentum flows into the system this way. Rotation start. Okay, so the last example I wanted to mention is this cascaded scheme. So this is a work of Mark Kuzik and his student. And so the idea was to take a number of Fabry-Perot cavities. So here 3 are shown. And this one, the cavity length is mechanically driven with a speaker, but the amount of light that goes through here is governed by the thickness and the wavelength of light. That light falls on a small piece of elastomer, which will respond to the light, and that'll change the length of this and resonance of this cavity, and then light going through that cavity is going to in turn affect the length of this cavity. So there's this complicated feedback system. And so this is interesting because it's now you see that it's a coupled system which combines sensing and actuation and logic. And so it's possible to get fairly sophisticated behavior from such systems, and Kuzik and co-workers are pushing ahead on that. So I think that's pretty much all I have to say. Summary, well, optical properties depend on the order parameter, and then by changing that biomechanical strain, one can control light to some extent. And the converse is that light can change the order parameter and give rise to strain and shape changes. And light-driven motors and other energy conversion devices are possible, and some of them look pretty intriguing. And one can combine sensing and actuation and make complicated integrated systems. So I think that there's a pretty inspiring number of potential applications that one can explore. Thank you for your attention.
Very nice lecture. Do we have questions?
Nice presentation. Thank you very much. You measured 270 hertz
Yeah.
flying the insect, but you had the continuous radiation in the material, yes? To get this 270. For pumping application, you switched off and switched on the light source, as I saw.
No, here, those CW. The laser was on all the time.
Okay.
This thing was just flapping. And
But
you can do it with sunlight as well, it turns
Okay.
out.
But for pumping application, you switched on and switched off the light.
That's right. That's
And
right.
what was the frequency of that?
Oh, we did that fairly slowly. I don't know, maybe a couple of hertz.
Last question. Did you do the modeling, dynamic modeling for calculation of this frequency?
No, that
Just you
remains,
measured.
that
Thank you.
remains to be done.
More questions?
I had a small question. The question was about Jake's, maybe I should ask Jake directly, but about the changes in the birefringence or the order parameter that you could obtain by stretching. What sort of size were they?
Oh, Jake?
I would have to look back at it.
Yeah. Not very different. I mean, we measured both epsilon and the index, and not very different from typical materials. But we have the number somewhere. Jake, the lab book.
More questions? If not, let us thank our speaker again.